Let me show very briefly what we had. So we did this. We did the first part of this tutorial, which are kind of trivial. It's what's called Doop 101. You can find it from the links on Slack, or if you look for the Doop framework and you find the repository on Bitbucket.
There's a link in the web page also.
Yeah.
They're going to get.
Well, but how do they get the web page? They have to get on Slack first. Okay. But if you find the readme.md file, the readme file from the Doop installation instructions on Bitbucket, it says consult Doop 101, which is the tutorial. And we did the first few lines of that, just a toy example of usage of data log. And we did not do the running and analysis part. We're going to do this after we discuss the theory a bit.
Should I sit down?
Yeah. And Wi-Fi over there for everyone who doesn't have Wi-Fi access. And I guess we can get started. OK, so what I'd like to do now is offer a quick high-level overview of what we do, the kinds of algorithms that we deal with, and the whole philosophy of the project, just so everyone is clear on the high-level bits. And then we'll get back down to the low-level bits of using data log and using the engine. And we'll look at actual analysis algorithms after I'm done with a high-level introduction. And then we'll go deeper and deeper in the next few days. So hopefully after we are done seeing the analysis rules late today and tomorrow, we can go and talk about context-sensitive pointer analysis, which is the element that distinguishes Doop, like the big thing that the Doop framework offers. So for now, we're going to talk about declarative static analysis with the Doop framework. And I'm Yanis, as you know. And the Doop framework was originally the work of Martin Bravenboer, who was my postdoc. And now he's at LogicBlocks, the company that develops the engine that we're working with, the data log engine. And George Castrinis and George Balaturas are my PhD students who are also contributors to Doop right now, as I am. So the four of us are pretty much the people who are supporting Doop these days. And what we do is static program analysis. And static analysis means that we discover program properties that hold for all executions. So we don't do testing, we do analysis exhaustively under all possible inputs. Anything the program might do, what's going to happen? So we're trying to discover such properties. Doop is a declarative framework, so that's what distinguishes it from all other frameworks out there for static analysis. Also, it's probably the most complete analysis framework for Java bytecode right now. So it's probably the most well-developed out there. So declarative means that the analysis algorithms are going to be written in a logic-based language. So you're going to see that we're going to have a specification that's based on logic. So later on in this seminar, I will discuss logic. I will do a presentation, an introduction to propositional logic, first-order logic. You'll see those things. But I don't want us to see those things before we have a hands-on view of what the rules are, how we can actually program in Datalog. Because I think it's much easier to understand Datalog as a programming language than it is to understand Datalog as a way to write arbitrary mathematical logic. And then we'll draw in the mathematical logic where we think it will help us do deeper things. So why does one care about Doop? I mean, OK, sure, it's declarative. It's actually not just declarative, but it's very powerful. It's very complete, as I said before. It's the most mature framework for bytecode analysis out there. And it's fast. So it's very competitive with all solutions that have been produced in the past. And of course, it's different in terms of architecture and has taught the program analysis community several lessons about how to architect analysis to make them scalable, what are the right analysis algorithms. And many of those ideas we will see slowly during the course of this seminar. So why do we do program analysis? And at the high level, I think you have seen the answers, probably not in such detail, but what I want you to remember is that primarily there are three reasons to do static program analysis. The traditional old-style reason is to do compiler optimization. So compilers do static analysis. But compilers do very simple stuff. Compilers do much more primitive analysis than the ones we will do. Compilers typically do intra-procedural analysis inside a single module, inside a single function. Everything we're going to discuss will be about a whole program image of the heap. So we want to go well beyond what current compilers do. And hopefully our technology in the future will be something that can be used in future compilers and runtime systems, meaning static and dynamic compilers. But right now, it's not just a plug-and-play thing. Compilers are perfectly happy with what they have, which is intra-procedural. So, but fundamentally, definitely we want to do static analysis so we can get optimization. More modern applications of static analysis include things like software understanding, program comprehension. Any tool that tries to give the programmer a good idea of what the program does or automatically changes the program in a way that preserves its semantics, it needs some good, sophisticated static analysis behind it. So if you're doing program slicing, if you want to say this statement of the program, what could it have possibly been affected by? So you need a good static analysis, whole program static analysis for that. If you want to do some refactoring transformation, if you want to do any kind of program query that includes the flow of objects, where can this exception object be coming from? You need static analysis. So that's pretty much the top application that we have today for static program analysis. And of course, we have bug finding. And there are lots of companies out there that have static analysis algorithms for finding security violations or regular programming bugs. So in the past 6 years, our work has been on developing Doop and other related frameworks. We'll talk about at least one related framework for LLVM, and we'll talk about many different branches of the Doop work. But these slides here are just about Doop, the core framework itself, although in the seminar we will see a lot more things. So Doop is a very powerful framework for Java pointer analysis. And pointer analysis is a specific kind of static analysis, but at the same time it's general because it's the mother of all sophisticated whole program analysis. Anything that you want to ask about a whole program, you will ask it on top of what a pointer analysis will do. So what we'll do today is we'll start with what pointer analysis tries to compute and how Doop tries to facilitate that. And as I said, it's declarative. We use the data log language. And we have done some work on client analysis on top of the pointer analysis. And we have lots of future plans that we will discuss later this week or next week. So what is pointer analysis? Pointer analysis is a static analysis that tries to compute the answer to the following question. What objects can a variable point to? So we have a program, and I've broken it up conveniently so it doesn't have any complex expressions, so it only has simple variables. And I want to find out for every little variable what objects it may point to while the program executes under all possible inputs. And of course, the first question here is, what does objects mean? I'm not executing the program, so what are the objects? And there's a standard abstraction, there's a standard idea that all sorts of static analysis use, and that is when we analyze a program statically, when we say an object, we actually abstract it, we represent it by its allocation site. Which means I have two allocation sites in this program. I have new A1 and new A2. This means statically, I only consider there are two abstract objects. There are two static objects in my program. That's not the case when the program runs. I mean, it could be that foo is executed 1 billion times. I could have 1 billion different objects that are allocated here. But at first approximation, all of those billion objects will be mapped to the same abstract object. So statically, one object here, one object here. And we will see soon we can add more detail to this static picture. But fundamentally, the first approximation is objects are identified, are represented by allocation sites, or objects are abstracted as allocation sites is a different way to put it. Or the object abstraction is an allocation site. That's a third way to put it. Any questions so far? Okay. So right away, we have this program. We want to compute the points to relation. The a variable inside foo, this a variable here, right away I know that it points to this abstract object. And the a variable inside bar, a inside bar, so this a in here, I know that it points to this abstract object because it's directly assigned to it. And if we try now to follow what the program will do, we will infer more stuff. What will we infer? The a variable inside foo gets passed as an argument to the ID function and gets returned back. This is a silly function that returns whatever is passed in. It's an identity function. So what I will infer is that the a variable inside ID will point to this abstract object, right? But also it will point to that abstract object. So that will be my next inference. A variable inside ID points to both abstract objects in my example. Right? So I'm following the program abstractly, what it does. Now, if I've represented the information like this, what goes back to B here and B here? Both of these abstract objects. So the next natural step of inference is to say that the B variable inside foo, this one, it gets back whatever ID returns. What does ID return? It returns whatever A points to. What does A point to? Both of these objects. So the B variable inside foo points at both of these objects. And the B variable inside bar, similarly, gets back the result of ID, which is just A. So it gets back both of these objects. So the B variable inside bar points at both of these objects. Does it make sense that I computed it like this? Or not exactly? Are we OK with going from this to that? Nope. OK. Why not? What troubles you?
Because foo B
Yeah.
could be only A1, right? Of type A1.
Well, that's true, but the logic here says ID, A inside ID points to both objects, and this gets returned, and whatever gets returned flows into this one, and whatever gets returned flows into this one. So it does make some sense to compute it like that, but it's not the fully accurate answer. It's not the fully precise answer. And in the end, any algorithm one comes up with will never be fully precise. This question, as a static analysis, it's an undecidable question, as are all interesting questions about the program, about complex programs. So there's no algorithm to compute this answer precisely. Every algorithm people come up with is an over-approximation. We compute more stuff than what actually happens in practice, every sound algorithm. Otherwise, we can be unsound and compute an under-approximation. But the traditional thing is we try to be over-approximate, to compute more than what can happen in practice. So we lose a little bit of precision, but we are guaranteed that we get everything that would be computed in practice. So here we lost precision right away, because the right answer, of course, is that B in foo can only point to new A1, and B in bar can only point to new A2. So is everybody with me so far? This is an over-approximate answer. It's the standard thing that a pointer analysis, a points-to analysis algorithm would do. But it's not as precise as it can be. OK. So what do we do to get more precision? So what we do to get more precision is Typically, there are many ways to do it, but the traditional way, the strongest way that people use in practice, is to use what's called context sensitivity. So we add to our pointer analysis, our points to reasoning, something called context, and we qualify local variables by context. And in this example, I'm showing a very specific kind of context, which is intuitive. We say the A variable inside ID when ID gets called by foo. And we distinguish that from the A variable inside ID when ID gets called by bar. And right away, this is enough to give us full precision for this example. Make sense? So this kind of context sensitivity, this kind of context, that we don't just remember information for variables, but we remember where the function that declared the variable was called from, that's called call site sensitivity. There are many different kinds of context sensitivity that we could have. It's not just that we'll have to have the call site here. I could have other things. Already, I say call site, and I put a method name, a function name. I could put an instruction number and have even more precision. What if there are two calls to ID inside foo? I could put an instruction number, which is the typical thing, and that would be even more fine-grained call site sensitivity. But in this seminar and in Doop in general, we will see that we can use other things as context. So one particularly good idea for context is what is the identity of the object on which I'm calling ID. And I'll leave that for later. We will explain all these ideas later with examples, and we will see how they're expressed in Doop and in the general formalism that we're working with. For now, what I'd like you to remember is that context sensitivity is the standard way, the most powerful way we have to make an analysis precise. Of course, we could make an analysis precise in many other ways. We could follow statement by statement all the set of values of a program. We could be flow sensitive, what's called, or even path sensitive to remember conditions. But these would be approaches that do not scale. They will never work for realistic programs. They compute way too much. So context sensitivity is a good compromise because it keeps just enough information to have some precision, but not too much. And we will see later on how Doop handles context sensitivity, and hopefully by the end of this week or next, you'll be perfectly comfortable with the idea of context sensitivity and different kinds of contexts that can be used, as well as with the base idea of pointer analysis. So for now, are there any questions here regarding pointer analysis or points to analysis, which are synonyms? Yes?
Somewhat related. So is either flow sensitivity or path sensitivity related to pointer analysis? To context sensitivity?
No. They can be entirely independent. You can have a context-sensitive algorithm that's not flow-sensitive. You can have a flow-sensitive algorithm that's context-insensitive. Okay. And then path and flow sensitivity typically are related. So path sensitivity is an elaboration of flow sensitivity. Okay. But flow path versus context, they're typically independent dimensions. Yeah?
The above points to analysis, the first one, the simple one, without context sensitivity, it looks too imprecise to be useful. But I guess that people use it somehow.
It's already more precise than the points to analysis that you will find in any practical compiler. This is what would be called, we haven't shown the full detail, we haven't shown the algorithm for this, but pretty much this standard approach, that's what would be called an Anderson-style analysis, and it's pretty good. It's not fully precise, but it's certainly precise enough to be usable in many contexts.
Oh, okay.
It's we definitely would love more precision.
Yeah.
But it may not be scalable at all with much more precision.
Oh, okay.
So the analysis that George is going to show you as soon as I'm done with the slides is a context-insensitive analysis that computes exactly that. So that's the naive analysis in the Doop source code.
And it's still useful, this one. It's better than nothing, I guess, or better than.
It's better than no points to analysis algorithm.
Yeah.
It's much better than any type-based algorithm, for instance, for computing, say, call graphs or anything like that. So it's better than anything that's strictly weaker, that's known to be weaker. Yeah?
When we say that an algorithm or an approach to resolve the points to set for a variable is context sensitive, this sensitivity may be a combination of attributes. I mean, it is up to me as a designer of the algorithm to combine the call site or the flow and come up with a...
That is correct. So we can have different kinds of context, and we can combine them, if that's what you're asking.
Yes.
And you can have different kinds of elaborations. So you can have context sensitive and flow sensitive, which is an independent dimension.
Yes.
And you can combine them.
Context sensitivity on two things, not only the call sites, not only from where the point I was called, I don't know, perhaps some other information, I don't know.
Yeah, but typically this will not happen in practice on two different axes, two different kinds of context sensitivity, because it's not going to scale at all.
Okay.
It means you're going to keep lots and lots of redundant copies of very similar information just to get a little bit more precision. So it may not scale. So for practical reasons, people don't do it. Theoretically, you can form algorithms that do it. So we have identified in the past some very specific combinations that give some benefit. But generally, if you're going to say, well, let's take one kind of context, call sites, and combine it with another kind of context, receiver objects, and combine it with a third kind of context. What are the parameters of this call? That's very quickly becoming unscalable if you implement it in an actual algorithm and you apply it on large programs.
Okay. And minor variation on the same question. Can we synthesize the results of such context-sensitive analysis from different dimensions? Given that we have a call site context-sensitive analysis, on top of the result of this analysis, we apply, I don't know, stack-based something or flow-sensitive analysis. Does this make any sense? What I'm asking?
They would be independent. So what you could do, theoretically, is run both analyses,
Yes.
and then only keep the results that appear in both,
Yes.
because the actual results have to appear in both. So in theory, you could do that. In practice, it doesn't really pay off. It's typically one analysis will be much better than the other, and you just use that one.
Okay.
But yeah, that's theoretically possible. In practice, doesn't often turn out to be a good compromise to run both. Okay, so we got the base idea of pointer analysis or points to analysis, right? Okay. So it's a complex domain. If you look inside the ACM digital library and you look for pointer analysis, you'll get some thousands of papers that are written. And the papers have complex terminology. You'll see things like context sensitive and cloning based and field sensitive, flow sensitive, things we mentioned before. You'll see keywords like alias analysis and pointer analysis and set constraints, lots of different terms. And what we tried to do when we first started developing Doop is isolate all that complexity so that we can express it in a nice, elegant way. And that's why we've chosen a declarative formulation for the framework. And the declarative formulation gives an answer to all of this complexity. So to see this complexity, here's an example of algorithms that are actual figures from a single 10-page pointer analysis paper. So we have one algorithm, and it says, here's how we're going to do the analysis. We have a graph of nodes that are statements in my program, and for each node, I will do some things. I'll enter them in a work list, and I'll have some logic here, and then I'm calling some other method, some other function. And here's one of the other functions. And here's another one, falsify aliases, and here's a third one, and here's a fourth one. And Now I need to shrink the font because this one doesn't fit. And here's another one, and yet another one. So obviously, what you get from this is that to read a single research paper, you need to read all of these algorithms. I don't think anyone has really understood that paper.
Was this a good paper?
It was probably a really good paper. It's written by people who are top experts in static analysis. Really top experts. They really know what they're doing. I cannot tell if it's correct. I don't think for the most part they can tell whether it's correct, that they have a good feel. Maybe one person who came up with all the ideas can kind of get it, but otherwise they rely on a fairly intuitive understanding of what's going on. There could be bugs at every level, but more than that, let's say it's correct. It's correct, you can test it like everything else. So you can be sure that it's correct. How do you know how something changes when at the very first step, your work list is implemented as, I don't know, a FIFO queue instead of a LIFO queue, or as a heap, as an ordered heap based on some kind of characteristic of the nodes? You have no idea. So you can change like one little thing in the algorithm and get completely different behavior. So that's the kind of thing that we try to distill in the Doop framework. We try to not have these endlessly complex specifications, but to have something that's pretty obviously correct. You understand exactly what's the logic behind it. And all the points of parameterization, where you get more performance or you get more precision, are very clearly marked. And you change one little function somewhere, and you know, now I'm introducing a new kind of context, and it transparently changes things everywhere in the analysis. So that's pretty much gonna be pretty much our philosophy for expressing all these analyses declaratively. Now, program analysis, it's not easy to see right now, but what you will see once we start getting into the rules is a domain of mutual recursion. Meaning, it's not enough to just write some rules for what happens when I assign variables, when I allocate new variables, and when I allocate new objects and assign them to variables, or when I assign things from one variable to another, or when I read object fields. I also need to know what happens with a call graph. When I call a function, which function actually gets called? Also, what's the total set of reachable methods? Also, what happens with exceptions? The exception that's thrown here, where does it propagate? The exception that's caught here, where can it be coming from? So all of those are little sub-analyses that all need to cooperate to produce the final result of the interesting relation that we care about, which is what a variable points to. In order to know what a variable points to, we need to know where exceptions go. We need to know where object fields on the heap point to. We need to know what are the reachable methods. We need to know what's possibly called from any specific call site. And all of those recurse with each other. So all our rules will deal with all those things. You will see declarative logic rules where they will use this information to compute that. They will use this to compute that. They will use this to compute that, and vice versa, etc., etc. You will see all this recursion everywhere in our rules. So to express recursion, Datalog is a language that's ideal. Because Datalog is a declarative way to talk about mutually recursive logic. So to do this, the very first step is we take the code of our program and we represent it as a database. So these are simple program statements, and we represent them as database tables. What could these tables look like? Well, in the simplest possible form, all I have here is allocations and move instructions, assignments between intermediate variables. So I can have a table for alloc, for an alloc intermediate instruction, and I know that I have an allocation of this new A object to A, an allocation of this new B object to B, etc. And then I have move statements that say B gets assigned to A gets assigned to B gets assigned to C. In general, I will do this for every single instruction kind in my language. So I have Any program I have, it's represented in an intermediate language. The intermediate language has, I don't know, many tens or hundreds of different instruction kinds. We will have a database table for each one. So we will represent all the text of the program as database tables. So that's the first thing that you will see in Doop and in other frameworks, our LLVM framework, for instance, that George is going to talk about, George B. Okay. Now, once we have everything in database tables, the next step will be to write our algorithms in a way that acts on those database tables. So Datalog will be a way to write recursive logic over these tables. And what will this recursive logic look like? Well, here are two Datalog rules, and they're actually the most general kind. You will see those rules in every analysis that uses Datalog for static program analysis. And I didn't say it before, some of you know it already, but there are lots of different formulations of static program analysis using Datalog. This is something that has been going on for 20 plus years. So there are frameworks like BDDB from Stanford that use Datalog for writing static analysis algorithms. It's not just Doop. There's good efforts at Microsoft Research that use Datalog for static analysis of JavaScript programs. So all of those formulations will have at some point these two rules because they're trivial rules for these things. So let's first look at the syntax of the rules and then we'll see what they do. So a Datalog rule, you saw it informally earlier today. What it consists of is two parts. There's a head of a rule, and the head will have a head relation or head predicate. So this is a logical relation or predicate. So this is something that we are inferring from this rule. Every time this rule fires, it will infer a new tuple, a new set of facts for this relation, for var points 2. And then every rule has a body to the right of this left arrow. And the bodies will contain body relations. And the body relations are using variables. And every time I have the same variable here, here's the intuitive way to think of it. It's a join variable, and I'm really joining this database table with this database table. So I already have computed a table for move. It's the current version of the move table. And there's the current version of the var points 2 table. To get the next version of the var points 2 table, I will join these two. I will join them on what common variable? On the from variable. I'll join two tables, produce a new one, and that's the new var points 2 table. So how does this join really work? What it really does is it does the intuitive thing that we expect for producing more facts. So these rules only add more facts as execution goes on. Clearly here we have var points 2 that uses var points 2, so that's one instance of recursion, but we can have as complex recursion as we want. We will see more complexly recursive rules in the future. So let's try to see these two rules in English, in natural language, and then try to follow an example. The first one is trivial. It says, if I have an alloc instruction that says this object is allocated to this variable, then I know that this variable points to this object. Obvious. And the second one is recursive, but it's still fairly simply recursive. It's what's called a transitive closure rule. So it says, if I have an instruction in my program that says the from variable gets assigned to the to variable, for instance, this move instruction here, B gets assigned to A, B is from, A is to, and I have already proven, I have already established in some way that from points to this abstract object obj, then I know that 2 points to obj. So that's also almost trivial, right? It just says whatever I know for from, I also propagate it to 2. Not the other way around. It doesn't say whatever I know for 2, I will take it to from. It says whatever I know for from, I will take it to 2. Every time there's an assignment from to 2. Right? Okay. So the first rule, all it says is I take the alloc table and I copy it here. And now the second rule, if we think about it in terms of database operations, like I said earlier, it says take this table, join it with this table, and what the result of this join is going to be added to the original one. Those are the extra contents of var points 2. And what am I going to join those on? I'm going to join those on the from variable here and here. So every time I find a common pair like this, from variable in var points 2 is the first one, this b, and from variable in move is the second one, this b. I know that b can point to this object. Now I will infer that a can point to the same object. That's the result of joining these two tuples in the standard database sense. Right? Any questions so far? No. Okay, so obviously just by joining these tuples, here's our next inference. We know that A now points to this abstract object. And if we continue with this, we keep joining this table with that one, well, we will join the first line with this line, and that's about it, I think. So we will end up with several more tuples. So now we will know that B points to new A, and then on the next step, because B points to both A and B gets assigned to C, C points to both, and this reaches a fixed point. So the evaluation of data log rules follows this pattern of always establishing more facts monotonically. We only add new things. Whatever was true before will stay true, and we add new things by joining tables until there's nothing more to add. And that evaluates exactly what we want. The logical consequence of this. Every time I see move and var points 2, then I can establish another var points 2. Okay? So who's troubled by this? Because this is a good point to be sure that everyone is clear with the kind of inference we have in the rules. So we're all good? Yeah.
So in the end, C points to C and B and A, or it's just the last line?
Points to all of them.
To all of them.
Yes. In the end, we infer that C can point to all three. May point to all three.
Okay.
Yeah, and in this particular example, it's actually, in this particular example, if you think of these three statements as executed in any random order, then it's an actual instance of pointing to everything. If you think of them as executing in this exact order, then this is an over-approximation. This is more than what happens in practice.
Or you could think that A gets B and B gets A are in an if-else statement. So
Yeah.
you don't know which one is going to happen.
Right. So arbitrary order can happen if you have these two in different branches, and then you can have a loop that goes through everything. Okay? Okay, so we got a very basic introduction to data log and how we do points to analysis in data log with simple rules, and we'll get to deeper rules in a second. Now, before I finish here, data log is a fairly powerful language. It captures the p-time complexity class, meaning that anything I write in data log can be evaluated in polynomial time. Anything that can be evaluated in polynomial time can be written in data log. In fact, we go even beyond that. We have exponential algorithms, but this is through a special feature of our data log, which constructs new objects. you can think of data log in two different ways. There's the database way of thinking about the language, and there's the logic programming way. So one can think of it as a restriction of Prolog. So it's Prolog without constructors, except in the limited way that we will look at them. And it's also an extension of SQL. So it's like SQL with recursion. So it's something between SQL and Prolog you can think of, but it's actually a very natural way to program. So we should be able to think of data log as fairly natural within a couple of days. After you do a few examples, after you manage to write some data log programs, and you see the flow of the language, I think it's going to be fairly natural. It's strictly declarative as opposed to Prolog, so conjunction is commutative. What's conjunction? Conjunction is that comma, that joining of two body predicates. That's really an and here. When this happens and this happens, this is conjunction. It's commutative. I could write it a different way. I could write the var points to first and the move next. Doesn't matter. The order of rules doesn't matter. Whether this rule is second and this first or vice versa, it doesn't matter. The result will be identical. So it's declarative in the sense that the engine that executes the program has full freedom to evaluate things any way it thinks is best, to produce a result fast, because it's going to be the same result no matter what the order of evaluation. And this is in contrast to Prolog, which has a very specific control flow, and it has cut statements. It has lots of specific search statements and an imperative order. So this whole thing increases our algorithm space because it means that we are free to look for efficient implementations for the very same specification. So when we write the algorithms, we only look at the specification at first, and then we think about how to execute this efficiently. So this is less programming and more specification. And Doop, as we said, is a data log-based pointer analysis framework for Java. It's very sophisticated, so it has lots and lots of different analysis algorithms, and it captures all of the different precision enhancements that people have proposed in the past. And it also pretty full-featured, so it supports the full semantic complexity of Java. So anything weird that Java has, most anything, Doop is trying to cover it. So it's a pretty full-featured framework. So I think this is roughly what I'd like to say today. We can do a comparison with other approaches, but I don't think this is very instructive right now. So I think this is a good stopping point for the high-level overview, because now we can go and see some specific rules, like a simplified version of the analysis of Doop. And once we're done with that, we can get back to the theory and see a very simple model of context sensitivity in this framework, and then go back and look at code and vice versa.
Okay, if you go a bit lower, you can find a subsection called running an analysis. So for this purpose, we have a really naive analysis written, just a few rules, I think like 10 rules or something like that, that mainly express things like Yannis showed you earlier with the var points to rule. And we are going to run this simple analysis on a jar file from one of our examples and see what happens. So the jar file that we are going to use is example.java. It's also in the repo. You can open it from the tutorial. It's just a fairly simple Java example. It has like 3 classes, I think, and a few methods. You don't need to understand the example. So first of all, we have to generate the jar file. Doop mainly analyzes jars. Even if you have just a single class file, you have to convert it to a jar. And there is an easy script that you can use in order to generate the jar file. So here I have the example.java, my example that you can see from the repo. And inside the bin directory, sorry. It's not here. Okay. Okay, it's not in the repo that you have right now, but it will be like tomorrow.
I think it is. Make jar.
No.
Maybe I haven't pulled here. Sorry. Yeah, I think that I merged it with the repo. Can someone check if there is a bin directory in? There is a bin directory. Okay. So under bin there is a mkjar that you provide a Java file and it will generate a jar file. It's just a Java CN jar command mainly. It's just a wrapper so you can facilitate things. So if I go to my example mkjar example Java, you will see that I have an example.jar here. Now, Doop follows the. Sorry?
So this is the file that we should change the target.
Yeah, if you want to build it with Java 8, you have to specify that you want to build it like with Java 1.7. So if you look at the directory structure in your repo, there is a top level directory called logic. Everything that's data log related is under that directory. And there is a subdirectory called analysis. And there you can find various analyses that we will look the following days. But the one that we care for now is the one that's called naive. And the main rules are the analysis.logic. We'll look at them in a minute. But just to have everything clear, we're going to use the naive analysis that you see here on the example.java that's in the Doop 1.1 tutorial. Okay. So first of all, let's run the analysis and then we can see what happens in a more detailed way. So, is that good?
Yes.
Like a level? Okay. Well, I can write it again. So, first of all, Doop has to be invoked from the top level. So if you are in a different directory, make sure that you go again in the top level of the repo. That's the only directory where you can invoke Doop safely. Then with the -a, you specify the analysis that you want to run. Doop will search for analysis with the same name that you provide here under the logic directory /analysis. So if I write -a naive, it knows that it has to find the directory called naive under logical/analysis. Then we specify the jar file that we want to analyze with -j. And the jar file is in my Doop tutorial example directory, the one that I just generated. Then we can specify a specific JRE that we want to analyze the jar against. So here I'm using --JRE 1.7 as a library. And what else here?
No stats.
Yeah. And also a small flag no stats, so no stats are generated just to see the main analysis run. So you saw that in a hurry this morning, but let's look at it again. There's a few steps that are involved here. First of all, let me make the fonts a bit smaller. So the first step is this one, fact generation. What we use in Doop is a suit framework. Suit framework is a framework. It's a complex framework. It can be used to analyze your program. It has some simple analysis, but we don't use should for the analysis components. But there is another thing that should can do, and that's to translate Java bytecode into Gimple. So when you analyze a jar file, or mainly the class files that you can find inside a jar file, everything is translated to bytecode. Okay, are you all familiar with bytecode? So bytecode is the way that Java handles translation from high-level source code to something that's understood by the VM. And okay, that's interesting.
Γιώργο, και εμένα μου έσκασε το δικό μας.
Yeah, I think I was changing a few things in the repo back a few months, and I didn't.
Did it work for anyone?
Same error.
Okay.
Well, I
Mine
think
was
it's
still
yeah, I think it's a different flag. I just
Okay.
I think the flags needs to.
Mine failed.
So let's hope that this works. So the first step is to invoke should, and should will translate Java bytecode to Gimple. Gimple is a language. I think should Gimple is created by the guys
of the suit framework.
of the suit
So
framework.
the suit framework is a compiler framework for Java. It's developed by McGill University, but it's pretty complete. Like for anyone who wants to do static analysis of Java, they start with suit and they build on top of that. So we use that in our front end to do the very first step of translating intermediate code into database table.
So Java bytecode is stack based, and Gimple is like a 3-address code, and we can use the 3-address code to generate our predicates and our input facts. So that's the first step. You invoke should, you translate from Java bytecode to Gimple, and then you generate the facts, the input facts for your analysis, and then the analysis starts. And the analysis crashes.
It's just because of the stats, though. The analysis works correctly.
Yeah, but
Why don't you run with a dash h option?
oh yes.
So we can see what is the starts option.
So it's yes.
Starts none.
Stats none. So I try to follow the way that Java C handles the specific arguments, but I didn't change the tutorial. Anyway, so after the first step, where should runs and generates the input facts for your database, then the whole data log analysis starts. There are a few steps there. I don't know, should we see them in detail right now, or should we leave them for later? The steps of the analysis.
I think we can leave them.
Okay, we can look at them at a different time. And after the analysis is run, mainly it imports the facts that you generated with should. It loads a few, well, few is a misnomer. It loads a bunch of rules. It computes facts the way that you saw in the slides earlier. And then you have a database with a few predicates like var points to, I don't know, call graph, reachable, etc. With the facts that the engine computed for your program. Okay. So here you can see that we have 3 steps in the analysis. The first step is where you load the facts that you generated with should inside your database. The second step is a prologue where you do some minor pre-processing, and the later stage, the analysis, is the main analysis stage where your rules run and you generate new things. Oh, did I go too far?
What's the error message you had previously?
No, it was the wrong flag. I was using the wrong flag.
Okay.
So this analysis, the naive analysis, does not produce the same predicates that all the rest of the analysis produce. So if you don't say no stats none, the flag that George put in, So make sure that people can see the flag so they
Yeah.
can replicate it.
So the flag
Yeah.
is,
So that's the run. That's
This
what
one.
you should use. So do
I will update
minus
the
a naive.
repo.
When you do minus a naive, instead of no stats, it's minus x stats column none. So before the analysis ran regularly, but then it tried to print some statistics, and it didn't have the right predicates for printing all the statistics it wanted.
So should we query first the database?
I think as soon as we're sure that everyone can run this naive analysis, so they have a database themselves,
Yeah.
we should query.
I also had some error.
What there?
So you also need to replace the previous Java command with the one which is you also need to set variables
And you want to variables the Jerry dir, which is the benchmark/Jerry directory, and you want the version, yeah. Oops. So maybe I should mention that for everyone else that might have a problem with Jerry 1.8. So if you're using Jerry 1.8 and you want to compile it using the mkjar thing for a previous version of the runtime, well, you open the mkjar script and you want the command in the end of the file. That command should replace the javac command that you had previously. And for this command to work, we need two variables, the Jerry directory and the Jerry version that we want. So say that you want to compile it against 1.7, you specify that here, and you need the Jerry dir variable, which should point to the same directory that you had the Doop Jerry lib. So if I have it correctly, I can use this. So this docs. So this will compile my example.java against Jerry 1.7 even if I have 1.8 in my machine.
Why don't you open it?
Sorry?
Why don't you open the script again so people can watch?
Yes. So I added these 3 lines. The first 2 are the variables that you have to change, and the last line, you just take it from the last line of the file. That's it if you have 1.8 in your system and you want to use 1.7 or 1.6 or something.
But it works with 1.8 anyway,
Which does?
the compilation.
Well, you would have a jar file that's compiled against 1.8 and you would analyze it with 1.7, so...
But it doesn't crash.
Well, it might not crash. It depends on the things that you have in your Java file.
I mean, it doesn't crash. No, I'm not asking. It works, but
Yes, I also ran
it's not.
Well, if you use something that's introduced in 1.8,
Yeah, of course.
this example won't crash because it uses simple Java commands. But if you use something that's new in Java 1.8, it might crash. I don't know. So, is everyone okay? Also, there is a nice flag in Doop. In case you are running the same Doop invocation many times, there is this ---- cas, so you can skip the shoot fact generation. That takes a lot of time.
It's not going to take a lot of time in the future, so
I don't trust you with the two flags. I need to check the manual first. Not the manual, the source code to be absolute true.
So, is everyone okay? Should I move on? What do you think?
so we can do some pop count, just inspect the database or something.
Yes. So one other interesting thing, when you run the analysis, you would see at the top level that you have a symbolic link called last analysis, which will point to the last database that was created from the last analysis that you ran. But otherwise, under the out directory, where is it? Well, I have it in a different place, but for you would be under out. Under the out directory, at the top level, you'd have an out directory. Under that, you could find a lot of directories, one for each analysis that you had run in the past, unless you delete it. So there's a bunch of directories there for every analysis that you run, and each time the top level last analysis link will point to the last analysis that you had run. So what should we do? Okay. So if I just do bloxbatch -db last analysis and do a pop count, we can see some interesting things. So we have all those predicates and more. Say instruction is an input predicate. It had a lot of entries. Do I see any output relation? So call graph edge source is call graph. That's the call graph that's generated during the analysis. There are a lot of predicates, as you can see, because even in our naive analysis, we have a few rules in the analysis itself, but we have the full input relations that every analysis can use, and Doop tries to cover every cornerstone case in the Java language. So you have like input relations for, I don't know, exceptions, handlers, assignment, monitors, whatever.
So as opposed to before, when we explore the database now, when you do pop count, you remember before we saw all those internal predicates, and we have very small predicates of our own, like parent and ancestor in the morning. Now we have lots of predicates that are all added by Doop. So there are all these tables in the database that Doop added, not just instruction and var, but also things that are results of actual analysis, like call graph edge source, or there will be call graph edge somewhere, I guess. All sorts of different instructions like virtual method invocation, load instance field, assign numeric constant, return, non-void, go to instruction, static method invocation. All of these things that you see are tables for different instructions, and some of them are tables for the results of the analysis. So I guess the bigger one will be some var points too or something, right?
There's a nice correlation between
Well,
the
not
sizes
too
and
big.
features of the language used in the program.
Yeah.
Well, it's not too big because it's the naive thing and it doesn't handle library.
Okay, so the naive thing only stays in the application. So var points 2 is small.
So should we look at the relations, at the rules? So if you follow the tutorial from the repo, you can see that two files are mentioned in the beginning. There is this file logic/facts/declarations, and also logic/facts flow insensitivity declarations. Those two files pretty much declare the whole schema of your input relations. So everything that you want to know about what inputs I can expect from the should fact generation step, you can find in those two files. And if you want to check, say for example, okay, I want to know what parameters the predicate for exception handler has, you can look at those two files and see the schema for this specific predicate and see what parameters it has, in what order, etc. So everything you want to know about your inputs, the schema of your inputs, is in those two files. Should we have a look at the inputs itself, the raw inputs that are generated by SUD?
The
does the syntax for the question mark mean something else?
No, it's just a character that you can have in your variables.
So we have the convention that we're following in Doop that all the variables start with question mark, but
it's nothing special.
it's nothing special.
It's just another character that's allowed in identifiers.
You don't even distinguish something from something.
No,
you
no.
just use a
Yeah.
question mark. Okay.
The same the way that you could have like an underscore in your variable names, you can have a question mark. Okay, let's look first at the output, at the input. So if I look at last analysis, which one is this? So if you look, there is a directory called facts under the directory under out /naive/ big hash number for the analysis that we run right now. There's a directory called facts, and under that directory there is a whole bunch of files with the facts extension. Those are the inputs that are generated by sudo. So, for example, say that we want to look, I don't know, at, say something, assign cast.facts. So you have things like, at this instruction, I think this is the line number, I don't even remember the schema myself. There is an assignment to this variable from this variable, and the type of the cast is this one, and all those happen inside this method. Okay, so this is the raw input that will be imported into Doop, and the analysis will run on top of that. And again, if you want to look at the schema, you can look at the two files that I mentioned earlier. But here you can find the facts that are generated by sudo from the jar file that you used when you invoked Doop. So it can be used for, I don't know, debugging, if you want to look at the facts themselves before you run the analysis.
Is this format the output of sudo directly? This is not simple. This has been processed by Doop to.
Well, it's
Doop has a front end called sudo fact generation that Anastasis and Dimitris are currently working on. So we'll look at this.
Sudo will translate from Java bytecode to Gimple, and there is a simple front end that we have on top of sudo that will take Gimple and will generate those. You can look at them as CSV, but we use tab for the
sudo is a
separator.
library. It doesn't have an executable. Think of it this way. It's a library. So we create a driver for this library. It's not big. It's like 1,000 lines of code. So we have a very simple thing that uses sudo to take the input bytecode and produce these tables.
Okay.
It just produces these tables in
It's
text.
CSV mainly,
It's CSVs mainly.
with tab separators.
Yeah, it's TSVs. So it's produced as TSV files, just so we can import them in the database. But this is just arbitrary formatting.
I was trying to clarify that this is not Gimple, just to.
This is
Yes.
not Gimple. This is our schema.
Yes.
This is our schema for what tables we want in the database, so we can do our analysis.
Well, we can look at Gimple later, maybe tomorrow.
So I can do the same thing that I was doing in the morning. While George is explaining one thing, I can use the projector to give examples of what he's explaining.
So, is everyone okay with running the analysis? No?
Okay, so here on the right, I just ran this naive analysis like before, and George was showing us the out files. So in the out directory, out naive, here, facts. So these are really all the tables. So it's not too many. I mean, for input, we have these tables here, which is what, like 40 tables, or 50, maybe 60. 57 tables. And you can look at any one of them. So, for instance, this is about if instructions. And it gives an instruction identifier which happens to have some informative text here, and then it gives numbers for where it is in the method or whatever. And I don't remember exactly the schema. If I wanted to find it out right now, I would look in the file that George talked about before, inside logic, logic facts declarations.logic. So this has the database schema. And in here I can look roughly.
I think you want to look at the flow and sensitive declarations.
Okay.
I think it's better.
Yeah. Because that part, that doesn't have if here. Because if is not flow insensitive.
Yes.
So really that's the table we were looking at before. It had an instruction identifier and then an index inside its method. I hope that's what we were looking at before. Let's look at the contents of these. Yeah, I think that was it. Yeah, so there's an extra pre-processing step between these facts and the actual tables, but pretty much it's the same thing. And I can print the contents of a predicate. Oh, that's going to print me 37,000 lines. And it's going to give me the schema at the top if I do print. Actually, no, it doesn't. Yeah, so all it gives me is the instruction identifier and the index inside the method. So, are there any questions?
So I didn't quite understand how the dot facts actually do map to the declarations. Does each and every field correspond to one of the parameters?
Yes.
Okay.
Every field, every column in this text of fact corresponds to the contents of a variable of a parameter of the predicate.
Okay.
So you just read them line by line. Each line is one tuple in their relation.
And
It's just that some of these relations, some of the relations that we will be using in Doop are really a little higher level than the facts. The facts are at the lowest possible level, and then we do some pre-processing and create some higher level abstractions, and then we run the analysis. So some of those you may not find them directly in the flow-sensitive declarations. You may look for them in other files. But you can just grep anywhere in the grep -r anywhere in the logic directory for the name of a predicate of interest, and you will find everywhere it's declared or used.
Okay.
So,
Okay, so we have run our first analysis.
yes.
And
we'll look
it
at
did something useful, presumably useful. It did something on some program. I mean, we did that earlier for the full Doop code in the morning. But here, this is something that we control a lot better than naive analysis. So now we can actually go and look at what the specification of the naive analysis looks like. Because this is something that we could have written right now, more or less. Almost.
So under the naive directory, you can see that there are 3 files. Delta.logic, I think it's empty. And it's there because, yeah, it's empty. It's a dummy file because the scaffolding needs it. And the delta and the declarations are pretty much useless. The main thing that you want to look is analysis.logic. So here, if I look, there's like 3, 4, 5, 6, 7, 8, 9, 10, 11 rules. We can look at them.
Let's make sure that everyone has opened the same file, because this is something that's worth reading at your pace.
So it's logic/analysis/naive/analysis.logic.
In your Doop home directory, under logic, you will find all of the interesting files, all of the interesting declarative files. All the interesting data log is there. So it's not that huge. This is something where you can look around. And in the next few days, we will be looking around that logic subdirectory. And we will be trying to understand different parts of it. So we all found that file, logic, analysis, naive. Okay.
Okay, should I move on? So the first few are just some simple rules. The first one, the big one, it's just to find the main method of your application. So if you want to look at it, so when you generate the facts, in some place you import the main class of your application that is extracted either from the name of the jar or from the manifest or from some other heuristics that Doop has in place. But when all inputs are imported in the database, there is also a main class predicate. So in that, you search for the main class, and then you search for a method with the right signature for the main function. It has to return void, take an array of strings, be public, be static. Has a simple name that's main, mainly. So pretty much this checks for a correct main method under your main class.
So this is boilerplate. That first rule is not really interesting. I mean, once you get used to Datalog, this thing is completely dummy, straightforward. You write it once, you never look at it again. So we can ignore the first rule, but it doesn't say anything fancy anyway. I mean, what it says is fairly simple to follow. When is a method the main method declaration? Well, under all of these conditions. So let's look at it here. Or, you can explain if you...
Like, just this.
Well, yes, but... Okay, so let me say it slightly different from the way you did.
Yes.
Trying to explain the inference here.
Yes.
So all that this is saying is, when is a method the main method? When a certain type called type is the main class, and a method descriptor has the string, and we have modifiers, public, static, which we will call public and static. And then all of those apply to the method. So the method is declared inside that type that we said has to be the main class. The method's name is main. The method's descriptor is this one here. The method's modifier contain public, and the method's modifiers contain static. So that's the logic. It's not too meaningful, but it's not too deep. And now it looks a little daunting, especially since we are introducing all these intermediate names. We say there's a modifier that we will call public, and its text is just public. Well, we gave it a name here. Why? Well, because that's what we need to use later. So, is this clear enough? And even if it isn't, it's something we can very easily push aside because that's not the essence of the analysis.
So then, after you have computed the main method of your application, you have the reachable predicate, which declares which methods are reachable in your application. So trivially, your main method is reachable because that's your entry point. And also we declare that if you have some class that is initialized, initialized meaning following the rules that Java has for the initialization of a class, and this class has a specific class initializer, then this class initializer is also implicitly reachable. So those two rules define the methods that are reachable in any context for your application. Your main method is reachable, and every class initializer for your class, for the classes that are initialized in your program, are also reachable. Okay. And then from here we move to more interesting things related to our analysis. So first of all, we group in a predicate called assign things that are similar to the move instruction but are somewhat different. So you have the simple assignment, the assign local. You assign something from a variable called to a variable called from. And if you look at the schema, you would see that the assign local predicate has a third column, which is the method in which this instruction takes place. But for our case, we don't care about the method. We just care about the two variables. I have an assignment from to to from. So we use this special variable, the underscore, which is the I don't care. I don't want to have a specific variable bind to this column. I don't care for its value. I want to ignore it. And then we infer an assign predicate from this. And also we have two other rules for the assign. So the first one says that if you have a call graph edge at a specific invocation side, and this invocation is inside a method, so you are inside a method called toMethod, or there is an invocation to some method. And this invocation at some index, say like the first index, there is a formal argument, formal parameter, formal. And in your invocation side, the first index, the first parameter, is the variable actual. So you can infer by those two that when you have an invocation and the formal parameter is formal and the actual parameter in this invocation is actual, you have a move instruction from formal to actual.
So formal is actually the meta variable?
Yes. And the actual is the parameter that you use when you invoke the method.
Okay.
So there's an implicit assignment from the actual in your invocation to the variable inside the method, right? And the other is the other way around. So when you return from a method, this method has a return value, and this method was called at a specific invocation site, and this invocation site put the result in a variable local. So you have the other direction of the assignment, from the return values to the local variables at the invocation side. Okay? So we use those three rules just to merge different commands, different instructions in your source code. That the main thing that they do is just assign an object from one variable to another. Okay, so far?
George, you're in trouble. No?
Should I move on? Yes.
Okay, intuitively this makes complete sense, but can you go over the syntax for the array, the formal parameter?
Oh yes, of course.
So
yeah, yes.
The syntax that must be the same as the actual parameter.
You're correct. Yeah.
But,
so this specific syntax here is what we call a functional predicate, you can think of it as another predicate. You could have it like formal, param, index, comma, to method, comma, formal. You could have it this way. It's the same predicate, but the difference here with the syntax in the first case is that this way we declare that this predicate is a functional predicate, and by functional I mean that for the combination of index and to method you always get this one value. Okay, for every combination of those two, you can think of the variables inside the brackets as the key. You get the same value.
So are there performance differences?
Well, I think they are, right? With functions.
What?
Performance difference.
I don't think that it's mostly performance. I think it will catch errors for you, because very often you will try to put a second thing in.
So this
the more
implicitly
you know,
applies a constraint that this specific pair of index and to method should only have one value. So if you try, when you do the, say, the import phase and you try to import facts, if you would import two different values for the same key pair, it would throw a constraint violation. And it's also an expressivity way. You can, what you have in mind that are functional, you can express it in your language to be clearer. But this would be the same with the version that you have seen so far with the parentheses.
Yeah, and really on this side, I'm editing to make this a little clearer. So I removed all the question marks. We just said this is just a convention. So don't let the question marks fool you, because at first it's hard to parse. So here, the same variables without question marks. And any other simplification that we may want to do, I can do on the right side. Really, the way you should think of these 10 rules, because it's really 10 rules that we care about here.
Well, less than 10.
It's 9, I think. Yeah. They start from here. But the main rule is the one we saw from my PowerPoint presentation. In the PowerPoint presentation, we said, if I have a var points to, and I know that the from variable points to an object heap, and we use the name heap for abstract objects, because they're heap objects, and I also have an instruction that assigns from to, then I know that 2 points to heap, right? And assign, in the slides, I called it move, because in the slides it was only the simple case of a local move instruction. But here, our assign is a much more complex predicate. So those are the 3 cases that George was talking about. That really, you don't apply this logic only to local move instructions, which is this one, assign local. You also apply this copying logic from one variable to another when you have a copy from an actual parameter to a formal. This is really just an assignment from the actual to the formal. And the same when you have a copy back from a return variable to a local variable that receives the return value of a call at the call side. That's this rule here. And of course, local assignments. So the reason we did these 3 rules, and I'm just repeating what George just told you in slightly different words. The reason we have these 3 rules is just to unify this case, because in the end, we're getting to this point, and we're treating all assignments the same. So this is not the full analysis of Doop, but when you see the full analysis of Doop, it's going to be very similar. This is a naive analysis. This is simple enough to explain. But in the next few days, when you actually see the full detail of the code, there are technical complications that some things will make you want to pull your hair out. But otherwise, it's okay. It's the same stuff.
So except the rule that Jan showed you from, it's the same from the slides when you have an assignment and a var points to from, and you infer something for the 2 variable. You have the base case, if we want to call it that way, from where the points to information starts. So that's when you have a new instruction in your source code. So yeah, when you have an assign heap allocation, that's the predicate that represents new instructions in source code. And these instructions assigns the new heap object to variable var, and this is inside the method in method. And we have inferred so far that this method, that the assignment, the allocation of the new object takes place, is already reachable. Then we can infer that var variable can point to the heap object. So here you can see also that we don't analyze anything in your source code, everything in your source code. We try to filter it out in various ways. Here we filter it out only to reachable methods. So methods that are not reachable are not analyzed in any way. And also, if at some point in the analysis a method is deemed to be reachable, then the few rules will fire, and then new information will be inferred. But until the point that this method wasn't known to be reachable, you don't have any fact generation. And then we have those two rules that simply handle when you assign to a field object, to a field in an object, and when you read this value from a field in an object. So the first one is when you have an instruction of the form, say a.fld gets b. And so this is the store instance field instruction. You have from a variable, so let me write it from, and this is base. So yeah, when you have a store instruction from a variable called from to the field of the variable called base, and then you have already knowledge that the base object the base variable can point to an object called base heap, and the from variable can point to an object called heap. Then you can also infer that the field of the base object can point to the heap object. Okay? And the rule beneath is the other way around. It's when you have something like 2 gets base.fld. So it's pretty much the same logic, but in the other direction. When you have a load instruction, that's the load instruction that I wrote above, and you have a var points to information for the base variable, and you have information that the field called fld in this heap object can point to a certain object, then you infer that also the two variables in the assignment may point to the same object. So those two rules are there to handle store and loads from fields in objects.
So I guess if we have only primitive types in our program, all these predicates are going to be empty, right?
Yes. And as a matter of fact, Doop doesn't handle primitive types. So for instructions that handle primitives, Doop will ignore those instructions. So yeah, if your method has only like computations about integers, it won't have a var points to result. Okay with those two?
There are big Java programs that use only primitive types to avoid garbage collection and stuff like that. So,
well, they can't be very big memory-wise, right?
Can you guarantee that there is no boxing unboxing automated by the compiler? I'm not sure. You can control it.
I don't know. Some language features may create heap objects anyway.
yes, runtime, right? So here we generate and stuff. So I don't think it matters.
Yeah, but when something is primitive, there's no point there. There is no heap allocation. So of course, if it gets ignored, it is expected to be ignored.
But this happens in the level of bytecode, right?
Python.
Yes.
So there are any implicit...
Yeah, if the compilers put some boxing there, you would have it in your analysis.
You already see that. So.
And should I move to the last rule? So the last rule seems as complicated as the first one, but it's not as stupid as the first one. It's more serious. So this last rule is used when we have a virtual method invocation. That's virtual, right? Yes. It's when you have an invocation of the form, say, let me get my facts straight, base dot to method Okay, you have an invocation, a virtual invocation in your code on a receiver object called base. Well, the variable is base, and you call a method called toMeth. And let's see first what are the conditions that have to hold. So first of all, this instruction is inside a method in method, and this method is reachable. So again, we don't analyze code that's not reachable. Then you have a invocation instruction. So here, this is instruction, which is bound to the variable invocation. You have an invocation to some method in method. And in this virtual method invocation, the base variable that's used there is base. So you have base dot something. And you know so far that base might point to a certain heap object. And you know that this object has a specific dynamic type, which is heap type. And you do a method lookup, essentially, for this invocation, and knowing the type of the object and the method signature that you are using there. And you find that this invocation, in the end, will invoke a method called toMethod. So here, the result invocation will handle like searching the hierarchy and finding the most recent overridden version of the method, depending on the heap type, etc. So you find here the actual method that's going to be called here, based on the information that you know from the objects that flow in the base variable. And also, another information here is that the method that you found that you're going to invoke has a variable called this, that is this variable. So if you know all those things, then you can infer three things. So here you can see that the head of the rule is these 3 lines. And again, with common we have conjunction. So with a single rule, we can infer 3 different things. The first thing is that toMethod is reachable, because we have proof that you have an invocation from a method that is already reachable to another method. Then you have a call graph edge from this invocation instruction to the method called toMethod. And also you have a var points to information, because inside the method toMethod, this variable is going to point to the same object that base did when you invoked this specific method. So this rule seems a bit daunting at first, but it handles virtual calls essentially.
So just for syntax, again,
it's a little bit magic, I think.
Sorry?
It's a little bit magic.
So let's start with the syntax. Everybody's clear that here we have 3 different things at the head of a rule, but this just means if these conditions are true, then all 3 of these are correct. So this is like breaking the rule in 3
copies,
rules, 3 copies of the rule with the same body and different head. So this is just a syntactic convenience that we put 3 things in the head. All 3 become true if the body is true. So simple enough, right? And the other syntactic conveniences we saw are underscore to mean any variable, any value, and that's the same as prolog. And then we saw functional predicates here, for instance, which is the same thing as just saying, invocation, comma, in method, but we just do it in a complex way just to tell the system that this is a function. There can be only one in method for this instruction. So every instruction has a single method that's it in. So this is a function from instruction to method. Now, there are a few things that are worth noticing here, and then we can come back to the bottom rule that's complex. So the first thing, we had this relation field points to. Where are we using this? Only here, right? So I don't really need field points to. It's only used at one point. Right? So it's just a convenience for me. It just materializes an intermediate table. So this concept that the field of an object, there is an object called base heap, an abstract object, and through its field FLD, it points to another object, another abstract object called heap. That's just a concept that's helpful for me. But my analysis doesn't really need it except for performance. I could take these three and merge them down here and eliminate the predicate. There's no field points to now. And that's really the logic. And the reason I'm writing it like that is so that we can see that this is very complexly recursive. It says, if my var points to has already proven three things, actually, like that, two things, that the base variable points to base heap and the from variable points to heap. Did I miss some instruction? No. The base variable points to base heap, the from variable points to heap. Yeah, I did miss something, sorry. There's a from as well. So what do we do here?
Well,
base heap.
No, in the store instruction you should change the base to from the variable.
I need to change. Where's from? Well, why did I get it wrong before?
Well, it's not base and base in the two instructions, load instruction and store instruction.
Okay,
They
so
are not
this
the
is,
same variable.
sorry, so this is base 2. That's
So
what
you should have the three var points to.
right. But is it base heap again? Yeah, it is base heap. It's base 2 and base
And
heap.
base
So that's
2.
really the right inlining. So now I fixed it. And you can see that's the real form of the loop, of the rule. If I see anywhere in my program a load instruction that's using a certain object base, like George is showing there. No.
Is it the other way?
Well, you can just put an intermediate variable somewhere. So so temp equals base2.fld. Yeah. And somewhere else, far away in my program.
Let me change the font up a bit. Okay.
And far away in my program, I have base.fld equals some other temp, and separate those two. That's what this really says. So I have a load, that's the first instruction, and my temp is 2, and I have the store somewhere else in my program, base 2 from a variable from, and now George is actually renaming it to match this. And now there's the recursion. So these two first lines, they're not too interesting. Those are input tables. They never change. Those tables are generated once and for all before data log really runs. The load instructions and the store instructions. They just represent things that existed in my original program, not things that are inferred by the analysis. But these three lines are interesting, because these three lines say, and my analysis has proven any way it wants, that base points to base heap, and base 2 points to the same base heap, and from points to heap, then I know that 2 will point to heap, which makes sense if you look at what this says. So this rule is all you need to do to handle loads and stores in your program. And it's recursive, so to prove more var points to, you need to have proven previous var points to. But to see why it's interesting, imagine that in Doop, we have 100 different ways to prove var points to. We have rules that say, if you have this way to deal with reflection, let's say, or with dynamic methods, with native code, this establishes var points to. Then you know that this variable points to this object. And with this rule, just in one fell swoop, we go in and we say, if I've proven any way I want, this var points to, that this base points here, this base 2 points to the same thing, blah, 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 with from, that's all I need to know to analyze the heap. That's all I need to know to find things that go into an object's field and then come out from an object's field. So recursion helps us. The monotonic nature of all these things help us. We really don't care how we got to the point of knowing any of these three var points to. As long as we know them, we infer more var points to. Make sense? And just to close again, I think we can just have a look at the rule at the bottom, because that's the most complex. And here again, we see recursion, but in 3 different ways. So we have, first of all, that reachable depends on reachable. And logically, this makes sense, because what does this rule say? If I'm in a method that's reachable, and that method calls another one, then that other one is also reachable. So very natural recursion. And how does it say that I'm calling the other one? If I'm in a method that's reachable and it has an invocation instruction in it, and that invocation instruction is over an object variable called base, and I have proven that base points to this abstract object heap, which has a type, and when I go and look inside that type, I find the definition of an overriding method called toMethod, then I'm inferring that toMethod may get called, it's reachable, and there's a call graph edge from the invocation instruction to the toMethod, and that this variable points to heap. So that's all that this very complex rule says. But we have recursion reachable and reachable, and then reachable depends on var points too. But also var points too depends on reachable. Here's one way. Var points too up here in this rule is only computed for reachable methods. So every predicate in the Doop specification depends on other predicates. You don't define just one. You define a whole bunch of recursive predicates, all in tandem. Call graph edge depends on var points 2. Var points 2 depends on call graph edge. Reachable depends on var points 2. Var points 2 depends on reachable. Obviously, every one depends on itself in complex ways. Var points 2 has a triple recursion on itself here. But we don't care. We don't think of it like that. We don't care how the engine is going to do this. The engine is going to keep adding stuff until fixed point, and we only need to think about the rules. And as long as our rules are correct, as long as our rules express what we want, that whenever the body holds, the head needs to hold, we're good. And we'll let it evaluate any way it wants.
It's magic,
It's not magic.
Yes,
It's the good
for
kind
the
of magic.
imperative word it is.
Right. Any sufficiently advanced technology is
Yes,
indistinguishable
yes.
from magic. Yes.
Does the way we write a rule affect performance?
Yes, it does. The way you order the variables affects performance. So really, for var points 2, if we had defined var points 2 in the database schema to be the other way, the performance on this rule could be different.
And
so if we had the base heap first and base second, the performance of this rule would be different.
And actually in Doop, the order is different.
In the full Doop, not in the naive analysis, but in the full Doop, this is inverted. But this is something that I'll talk about in 2 days or so. I'll show all the optimization logic that goes in. But let's first...
Either way you write it, the answer is the correct one. It's just performance-wise optimizations.
And also it's an implementation detail, so some other engine might have different trade-offs.
How it evaluates facts, how the engine evaluates facts to determine whether the rule applies, I suppose. That's the trick.
Yes.
Where are the more
Selected one.
Yes.
Yeah. So it's query optimization. It's just
Yes.
this is a big join. All this is a big join.
Yes.
This is a join of 7 tables.
This is it.
If you think about it. So every query optimizer, when it needs to join 7 tables, it needs to decide which 2 it's going to join first, and then what's going to be the next one, etc. So it's standard database stuff, but it's also like what indexes exist.
So the order of the variables affect the indexes that are created.
So we'll get to that. It's we have very good slides, and then we'll look at it in the code as well.
About the functional notation with the square brackets,
Yes.
is there an analogy to relational databases where I don't know, something like a foreign key
Yeah.
constraint is generated.
Exactly.
Okay.
Well, it's not a
It's
foreign
not a foreign
key.
key,
It's a primary
constraint.
key.
Yeah.
It's a primary key there. It says this is a table instruction method,
Where
and its
invocation is the key.
primary key is invocation.
Can we express foreign key constraints in the data?
Yes. With right arrows.
Right. At the declaration level.
You can say that this predicate should have a variable and this variable should exist also in the other predicate.
Okay.
And or maybe the opposite, that there shouldn't exist a variable here that's not found in the other predicate. I think we do that with sanity rules.
Yeah. Probably.
It is extremely modular. The way that it abstracts away the details, as you saw it with the var points too. I have an assign, I don't care what assign means. I begin with assign false, whatever, or always fail, and then I gradually add the new rules. It keeps on growing.
Yeah. I mean, that monotonic element is key. We only add more things.
Yeah.
So we keep, the rules are firing just to add more facts all the way until fixed point. And that's what makes the whole thing modular. You add more rules, well, great. The more rules mean now you have more ways to prove more facts. So yeah, maybe if you add more rules, you're going to be able to establish even more of our points to relations.
Modular is the only way to keep a mental state of what is going on. If it wasn't modular,
yes, exactly.
Otherwise, the first slides you saw with the algorithms.
Yeah, Doop has right now over 1,000 rules. So yeah, you wouldn't be able to keep track of those because they're so complexly recursive.
Are we going to talk about linear regression? So
No.
I think some rules are transformed to linear regression automatically, right?
No. Not in the 3.0 engine. No, not in the LD3.
Yeah, it happened only on the.
But how does it transform it if I haven't written it as?
Yeah, it detects some basic case.
Άμα το κάνω σωστά.
495.
Well, I think I'm missing something here, but
Why don't you do all of logic?
all of the
Yeah. And also,
where a few rules are like they have multiple things in the head.
And I don't know whether it is too early to ask it, but whether you decide to use a context-sensitive analysis, it's up to you, of course. Do this modify the rules?
Well, we can see that tomorrow because
So-
there
I
is
just understand.
really, Doop, all the rules, the naive analysis is just for demonstration purposes, but when we go and look at the real analysis of Doop, you will see that all the rules are written in a context-sensitive way. So all of the rules have context in all the predicates. So, for instance, let me show you. In full Doop, this becomes CTX, comma 2,
what I have here.
8 CTX, comma he. So both the abstract objects and the local variables, they have context. One of them has a calling context, the other has an object context.
Yeah.
So all the rules are written in terms of context. But then we have these functions that we parameterize. And a context-insensitive analysis just means
Just
take a
looks-
context-sensitive one and create a function that keeps returning the same thing.
Yeah,
It doesn't create new context. There's only one context. So that's a context-insensitive one. And then the context-sensitive ones create different kinds of context.
I think this one if you want to.
Okay. Wow.
Well, there are some comments there. Yeah.
So mainly you just care about the
Yeah, but that's exactly the same rule as the bottom one there, pretty much.
just have more columns for the context here. And also reachability is inferred in a different place for every call graph edge. And there is this opt virtual things that you are going to look at a different day, I guess.
Yeah, I mean that opt thing, everything that begins with opt in the source code is just because it would normally be without the opt, but we use an opt predicate just to invert the variables. So you see opt virtual method invocation base on the left, whereas we have virtual method invocation base on the right. But really that one is a function. This one inverts the indexing order. We'll talk about indexing and optimizations later.
Opt is for optimization, not for
Yeah.
option.
Yes.
No, opt is for optimization. Yeah. It's just a predicate that exists for optimization purposes, not because it has a meaning otherwise. So I
should
think-
we wrap up?
Yeah, I think we should stop here. We did quite a bit for today.
And we can continue tomorrow with a few queries and then we can look at context.
Yes.
So I will try to mainly post in Slack at least the few commands that you should have for the environment, the few verbs that you should export. They are also in the tutorial, but I guess it's better if it's in a single place with the correct values. So I will do that. And I guess anything that you want to ask, you can write in Slack.
Thank you, George.
Yeah.